11.1 example 2 takes us to a particular type of notation. I'm just going to kind of go back. This is in your textbook. And the notation itself is the idea that if we take n items and arrange r of those items where order matters, then the number of arrangements is what we call n pick r. So that capital P is for permutation. Permutations are ordered arrangements where the order matters. N is the number of items total, and R is the items that we're actually selecting to, arrange them. Now, in the previous question, we had in the middle, in example 1, in the middle, we had 5 people and we were arranging all 5 of them. And I talked about that if I have 5 objects and I arrange them, I get 5 factorial, which ends up being 120. I'd like to show you that if I did have, 5 pick 5, so I have 5 objects, 5 people in this case, and I'm arranging all 5 of those people where the order matters, then based on that formula, this would be 5 factorial over, in a bracket, 5 minus 5 factorial. Now, what this is equal to is 5 factorial. 5 minus 5 is 0. And really importantly, I'm not dividing by 0 here because 0 factorial is 1. So I end up with 5 factorial over 1. So we know that it works, right? We did the last example using the fundamental counter principle, and I'm getting the same solution there. Now, it does give the restriction that n has to be a natural number. So that's 1, 2, 3, 4. You have to actually have items. There is another restriction here that n must be greater than or equal to r. I cannot arrange 10 items if I only have 2. So, you're not going to run into a question like that, but I think it is important that the number of items we have has to be equal to or exceeding the number of items that we're actually arranging. Quick reiteration on the bottom here, it talks about what factorial is. This particular link here I will put on Google Classroom. It has an interesting explanation as to why 0 factorial is actually 1. We are going to now solve the problem with it. And it's really important that this is on your formula sheet, but you have to know where that is. And I'm going to tuck it in, maybe right up, we'll do it right here, that n pick r is n factorial over n minus r in a bracket, and then factorial after the fact. All right, so A wants us to evaluate 9 pick 4. So 9 pick 4, if we follow the formula to the left there, that is going to be 9 factorial over 9 minus 4 in a bracket factorial. Now, full disclosure, you have a button on your calculator. I'm going to show you that now. I'll show you an algebraic way of doing this as well. If we grab our calculators to access that factorial, what we do is we type in n first. So 9 was n. Then I go to the math menu, over to probability, and there's my NPR right there. So it's very, very much the same notation, which is nice. When I hit that, the calculator picks up whatever number is in front as n, and whatever number is behind as r. So if I want to do 9 pick 4, I get 3024. So a lot of different possibilities. I'd like to show you that we can also check that by doing 9, go to our math button, over to factorial, divided by the brackets, very important. So 9 minus 4, and then I'm going to put that factorial after there. And we see that we get exactly the same value. But one last thing that I'd like to show you, and we'll do the math behind this as well, that with a bit of simplification, which we're going to do in a second here, if I took 9 factorial and divided it by 5 factorial, I would also get that 3024. Now, I think the logic behind why that is pretty, pretty steady. That if we do the bracket first, 9 minus 4 is 5. And that's going to be really important that we are able to rewrite this factorial, or at least clean it up a little bit. And the first way that we're going to do that, I'm going to kind of drag this over here because there's a couple more things we're going to do. I'm going to rewrite that as 9 factorial over 5 factorial. But I don't want to have to rewrite the entire list. So what we can do instead is we can simplify factorials. And the way that I'm going to do that is I'm going to write 9 factorial as 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then I could write 5 factorial as 5 times 4 times 3 times 2 times 1. And at this point, students will typically see, okay, so the 5 cancels, it's a common factor. The 4 cancels, the 3 cancels, the 2 cancels, just trying to use different symbols to show that. And then finally, the 1 cancel. And we get 9 times 8 times 7 times 6, which is equal to 3024. Right? That's a very algebraic way of doing that. But there's one more thing that we're going to have to get used to. I can take 9 factorial and write it as 9 times 8 times 7 times 6 times 5 factorial. And the reason I can get away with that is that this piece right here that is unfortunately a little scribbled at this point is 5 factorial. right? It's 9 times 8 times 6 times, sorry, I missed 7. 9 times 8 times 7 times 6 times 5, 4, 3, 2, 1. But instead of writing that 5, 4, 3, 2, 1, I can leave it as 5 factorial. And the advantage is that 5 factorial cancels with 5 factorial. And this might seem like, okay, that's great, who cares? It is very important you are able to manipulate factorials. And it is that unfortunate, I'm going to write this, that 4 factorial divided by 2 does not equal 2 factorial. You need to have identical factorial terms or factorial factors in order to cancel them. And so a lot of chapter 11 is about manipulating these factorials with the intent of simplifying them. And the reason why this is so important is a lot of things in calculus are defined or, proven using factorial notation. So we have to get used to it. All right, the next problem here, and I'm actually just going to pull this onto a new page because I think I wrote far too much here. I'll take B and C. We'll do them both on the next page here. If we look at B, it wants us to show that 100 factorial plus 99 factorial is equal to 101 times 99 factorial. Now it says, and I always laugh at this, without using technology, your calculator cannot do 99 factorial. It is far, far, far too large. It'll give overflow. So we have to use this, or we have to solve this problem without technology. And the best way that we can do that is to think about factoring. If I have 100 factorial and 99 factorial, right now I can't factor anything out. But I know that 100 factorial is 100 times 99 times 98 times 97 times, and all that is going to continue until I have 3 times 2 times 1. But instead of writing all of that, what if I wrote it as 100 times 99 and then I put the factorial there? Because 99 times 98 times 97 until we get to 1 is 99 factorial. And the advantage of doing that is I can rewrite that top line and say that 100 factorial plus 99 factorial is 100 times 99 factorial plus 99 factorial. And the reason why that's an advantage is now both terms contain 99 factorial, which means I can factor it out. 100 times 99 factorial divided by 99 factorial is 100, and 99 factorial divided by 99 factorial is 1. And this leaves me with 99 factorial times 101, which is what the question wanted us to show. The reason that this is in here is because we need to get comfortable with the idea that we can manipulate these expressions with the intent of simplifying and solving, which is what we have to do in C. C needs us to solve an expression, an algebraic expression that involves the factorial, and that's n pick 3 is equal to 60. Now, I did talk earlier about n had to be greater than or equal to r, so there is a restriction in this case. We know that n must be greater than or equal to 3. We also know that n must be a natural number. So n could be 3 or 4 or 5 or 6 or 7 or any number in that list. And that is valuable because if you're doing this question and you solve it, you get some weird quadratic, whatever it is, and you end up telling me that n is equal to 6.5, that's not an appropriate answer for n in the context of permutations. We do not or will never ask you to arrange 6.5 items, because that 0.5 item might be, half as big as the others by volume, but it is still an item that can be arranged. So it's really, really important that both n and r have to be natural numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that keeps on going. Don't stop at 10. Now, the way that we're going to solve this is we are going to rewrite it using our factorials. So n pick 3 is n factorial over n times n minus 1. Oops, got ahead of myself there. So it's n factorial over n minus 3 factorial, which is equal to 60. Now, in order to solve this, and students do find these questions tricky, what I have to do is somehow get rid of the factorial. I don't know what n is, but I do know that to write n factorial, it would be whatever n is times 1 less, times 1 less than that, times 1 less than that, and that pattern would continue. But instead of continuing, I'm going to leave the factorial here, because now the factorial in the denominator, the n minus 3 factorial there, this will cancel with the n minus 3 factorial in the numerator. It is very important that you need to have the exact same expression with that factorial after it in order to make that cancellation. If they are not exactly the same, this technique will not work. Now, what this leaves me with is n times n minus 1 times n minus 2 being equal to 60. That is a cubic equation because the n will have, the highest degree will be 3. And in order to solve this, we should expand. I'm going to write this as n times n squared minus 3n plus 2. That's equal to 60. So n cubed minus 3n squared plus 2n minus 60 is equal to 0. From here, we have to solve this as we would any other cubic polynomial. What I'm going to do is I'm going to do this one graphically, and then we'll do an algebraic one a little bit later as well. What we would use, and I think the easiest technique is certainly graphically, but if I grab my calculator, I'm going to put that into y equals, and I know that I have to use x instead of n. So x to the power of 3 minus 3x squared plus 2x minus 60. And then because of the restrictions on n, I'm not overly worried about, negative x's. I know they have to be positive. When I graph this then, the x-intercepts of this graph will be the solutions of that cubic. And we get this. So it looks like it's only crossing at one point. It is a positive leading coefficient cubic, so it does have that m behavior, something like that. I would like to maybe just grab a glimpse of the entire function so you can see it. I'm going to make my my y min negative 100, just to try to catch that full cubic polynomial behavior. And there we see the actual cubic shape, and it only has one x-intercept. So you need to love when that happens because it means that there is only one solution, and typically this happens. In order to find that solution, I'm going to use second trace and then 0. So I'm going to put my cursor to the left of it. That's fine. To the right of it, I'm just going to tell it go to x equals 9, and then my guess is right here, and it tells me that 0 is 5. Now, there is another option, which is to use your table, and you can literally type in. We know that 3 is the lowest number. I can check 4, I can check 5, I can check 6, 7, 8, and so on, and we can see pretty clearly that it is not going to go back near to 0. So x, or n, is equal to 5 as our only solution. Now, what that does mean is, we use this graphical concept. So I am going to say that n was equal to 5, which we can summarize as 5 pick 3 is equal to 60. Now, again, giving meaning to this is really, really important. What 5 pick 3 equals 60 means is if I have 5 objects, and I arranged 3 of them, where order matters, there are 60 unique arrangements of those 3 objects. And it's really, really important not to forget what permutations actually tell us. We can get lost in the algebra of factorials, but we want to make sure that this gives us the ability to quickly, essentially determine odds for a lot of different, games of chance. It doesn't have to be gambling, but if you're playing a board game or crib or Dungeons and Dragons, whatever it is, if there's a random chance involved, it's very useful to know the odds of success or maybe, the chances of failure as well.